Hi everyone, welcome back to the Big O series. Today, we're talking about another very important complexity class, O log n, also called logarithmic time complexity. In simple terms, O log n means that with each step, the data left to process is cut in half. That makes the algorithm grow very slowly, so even with huge amounts of data, it stays efficient. You've probably used this idea before. Imagine looking up a word in a dictionary. If you go page by page, that's linear search, O of n. But instead, you flip to the middle, check whether your word is before or after, and then only search in that half. Then you flip to the middle again and repeat. Each time, the search space shrinks by half. That's O log n. To make it more concrete, let's look at a binary search example. Remember, binary search only works if the array is sorted. Suppose we have a sorted array, and we want to find the number 11. First, we check the middle element, which is 9. 9 is smaller than 11, so we only look at the right half. In that half, the middle element is 13. 13 is larger than 11, so we switch to the left half. Now there's only one number left, and it's exactly 11. In total, we only looked at 3 elements instead of all 9. Here's how this works in Python. We use 2 variables, left and right, to mark the current search range. Each loop, we check the middle element. If it matches the target, we return the index. If the middle element is smaller, the target must be on the right, so we move the left boundary to middle plus 1. If the middle element is larger, the target is on the left, so we move the right boundary to middle minus 1. The loop continues, cutting the search space in half each time. Eventually, we either find the target or the range becomes empty, in which case we return -1. The key is that every step cuts the search range in half. That means the maximum number of steps is about log base 2 of n, so the time complexity is O log n. Even if the array has millions of elements, the number of checks is only around 20. And binary search isn't the only example. Many other algorithms have O log n complexity. For instance, searching, inserting, or deleting in a balanced binary search tree, inserting or deleting in a heap, some stages of divide and conquer sorting algorithms, and a very practical one, database indexes. Most relational databases use B trees or B plus trees as indexes. When you look up a record, the search starts at the root, and each level down shrinks the range by a large fraction. The steps grow in proportion to the logarithm of the data size, so the search complexity is O log n. That's why databases can handle huge amounts of data and still return results so quickly.